Now we've separated the equations for the internal states of the hydrogen atom into two parts. One is the angular part we've already solved with the solutions that are the spherical harmonic functions. These make up the angular aspects of the orbitals that are the wave function solutions of the hydrogen atom problem. The second part is the radial equation, which will give us the behavior as a function of distance from the center of the atom. This equation can be solved by some straightforward, though rather mathematical techniques. The solutions to this equation are well known and well understood, and it's easy to check that they work. Though the technique that allows us to construct these solutions, a method called series solution of differential equations, is quite a useful method, it's not particularly likely that you will come across many other problems that require you to use them. So here, we're largely going to avoid that mathematical detail of how we get to those solutions. Instead, we will basically state what the solutions are and concentrate more on trying to understand what they mean in a physical sense.
So now let's look at these radial equation solutions. Remember, we had used a separation of the hydrogen atom wave function into radial and angular parts for our internal states. And we had rewritten the radial part using this alternative way, and we had therefore obtained this radial equation here. And we know already from the solutions of the spherical harmonic parts that L is 0 or some positive integer. Well, now we're going to choose to write our energies in the following form: minus the Rydberg divided by n squared, where for the moment n is just an arbitrary real number. Of course, in the end we're going to show it's an integer, but for the moment it's just an arbitrary real number. So there's nothing to stop us from choosing to write our energies in this form here. We are presuming that this energy is actually going to be a negative number. We'll define a new distance unit for the purposes of our algebra for the moment. A distance unit S is equal to alpha times r, where this alpha parameter is given by this formula here. And again, because EH is going to be a negative number, we think it's all right to have this minus sign in here. This alpha should still be a real number. So this is just for algebraic convenience. Therefore, with those slight changes, we get this equation. This is exactly the same equation as we had before, but because of our minor changes of units, it looks a little simpler. Then we write, let's presume that this chi of s function is s to the little l plus 1 times some function capital L of s times e to the minus s over 2. Now, incidentally, this capital L here is nothing to do with the angular momentum operator. It's just because of the particular name we're going to end up with for these functions that we also are using the letter capital L here, but don't confuse this with any solutions of the angular momentum equation. This is a standard notation, though, for the functions we're about to come up with. So this is just some function L of s, and remember s is really just the radius here in a slightly different dimensional form. So we've really got radius to the power L plus 1, some function of the radius, and e to the minus something proportional to radius over 2. So with that presumption, substituting in here, we get this equation. So that's merely substituting this into the equation at the top here. A little bit of algebra, we'll get this equation here. Now, that equation can be solved by a technique known as series solution of differential equations. And basically what one does is propose that there's some power series in this variable s, and then substitute that in here for this function L and see what happens. And the key thing we have to do is find a way of setting up that power series so that it does not go on forever. We want the power series to terminate at some finite power of the variable s. Otherwise, the function is not normalizable. So the power series will go on forever unless we satisfy some termination condition. We need it not to go on forever because otherwise the function would grow arbitrarily and it wouldn't be normalizable. So there are criteria we come up with now when we construct this power series solution for this equation so that the power series will terminate at some finite power of s. And that in turn requires that this n is an integer and also that it's greater than or equal to L plus 1. So this is actually relatively straightforward to work out, but it takes a bunch of algebra to do it. If you propose a power series for s, put it in here, and if you want that power series to stop at some point, then you will need to have n as an integer and it will need to be greater than L plus 1. So the normalizable solutions of this equation turn out to be these finite power series. They're known as associated Laguerre polynomials, and they have this form. Now, on the face of it, this looks rather complicated, but realize what it is. It's a sum over a bunch of powers of s. So we're going from s to the power 0, q equals 0, with some factor in front of it, all the way up to the term s to the power n minus L minus 1. So it's a polynomial of degree n minus L minus 1. And these are factors out front. They're straightforward to work out. We just evaluate these factorials. So from this expression here, you could write down for any particular values of n and L exactly what this polynomial is. And it would be some polynomial that went up to the highest power, s to the power n minus L minus 1. So from this formula, you can write down the associated Laguerre polynomials if you want to. Or equivalently, in the notation in which the Laguerre polynomials themselves might actually be written in a mathematics book, we could write it like this. But these are actually exactly the same expressions, just with a slightly different notation. So now we can work back to construct our whole solution. We've actually now solved the whole problem. In our definition here, these L functions were the associated Laguerre polynomials. So we put those in. And we note that s we had defined was this particular variable here. So we can work backwards. We knew what our radial solution was. And if we work backwards to get what this r is, then this is what the r looks like. And we've not put in a normalization factor here yet, but this is basically what the capital R function looks like now. And equivalently, since r and s are just proportional to one another, this is really a function proportional to s to the power L times all of this on the right. We can formally now normalize these, so we could formally put in a normalization coefficient so that our r function was 1 over a times all of this here. The full normalization integral of this wave function would be this expression here. Everything on the right would have to integrate up to give us 1. That is, the modulus squared of the wave function integrated over all space would have to give us 1. Because we're working in spherical polar coordinates, the volume element that we end up working with in this equation is this r squared sine theta d theta d phi dr. But that's just coming from the spherical polar coordinates. But we've already normalized the spherical harmonics, so we don't have to do that again. So we're left with the radial normalization. And the integral that we would be left with would be this one here. We could show, with a little bit of effort, but just relatively standard mathematics, that the integral of everything inside this expression would just come to these factorials on the right-hand side. So the normalized radial wave function would become this expression. So basically, r to the power L, a Laguerre polynomial of this type, and an e to the minus r over n times the Bohr radius. We write these wave functions now using the Bohr radius a0 as our unit of radial distance. So we've got a dimensionless radial distance just for convenience. So we use a new coordinate, rho equals r over the Bohr radius. And we introduce some subscripts here. Specifically now we give names to these. N is the principal quantum number. And remember, we deduced it had to be an integer. and it had to be greater than or equal to L plus 1. And L is our angular momentum quantum number, the same one we had before from solving the angular momentum problem for the L squared operator. And we use these to index the various functions now that we can write out. So here are some of the functions. Explicitly then, for n equals 1, the principal quantum number equal to 1, and the angular momentum quantum number therefore has to be L equals 0, because n has to be greater than or equal to L plus 1. So if n is 1, L has to be 0. Then we get this function, which formally is in this form. So it basically is a function that simply falls off exponentially with distance, and that falls off with an exponential decay length of the Bohr radius. Remember that rho is just the actual physical distance, r divided by the Bohr radius. So here it is. This is the function in radius that corresponds to the n equals 1, L equals 0 state. If we go on to look at the n equals 2 states, then here they are plotted up, and we'll show what they actually are. For the L equals 0 state with n equals 2, then we have this red function here. So it's basically 2 minus the radius in Bohr units times e to the minus the radius in Bohr units, but now divided by 2. So this function goes out further. The exponential decay is slower now that we've gone to higher n. For the n equals 1, it was just e to the minus rho. Now it's e to the minus rho over 2. So the overall exponential decay of this function is slower. And there's also a 2 minus rho multiplying it. That means that this function goes through a 0 here at rho equals 2, at 2 Bohr radii away from the center. For the L equals 1 radial function, it's this blue curve here. Note that now this function is 0 at the origin because there's a simple rho out front multiplying it. It falls off still at large distances with the same exponential factor, which is e to the minus the radius in Bohr radii units divided by 2. So the same kind of exponential decay. But this function never goes through 0. It may be 0 at the middle, but it never goes through the axis. For principal quantum number n equals 3, here are the various radial solutions. For L equals 0, the red solution, then the function is this quadratic here times the exponential of minus rho over 3. So this is falling off even slower than the n equals 1 and n equals 2 states. And this quadratic here has got 2 zeros, so the red curve goes through the axis twice. For L equals 1, the blue curve, we have rho times 4 minus 2/3 rho. So this goes to 0 at the origin here at 0 radius. It has another 0 when this factor equals 0. And it also falls off with this exponential minus rho over 3 now. And for L equals 2, we have the orange curve. And that is rho squared times the exponential of minus rho over 3. So it also starts at 0 here, grows, and then decays with the same exponential. We can look at the probability densities that we can calculate here, and I've plotted on this particular picture, first of all, the n equals 1, L equals 0, m equals 0 function. And this is the cross-section taken at y equals 0 in xyz space. So you're looking at the xz plane at y equals 0, cutting through the middle of the hydrogen atom. This is known in the standard nomenclature as a 1s state. So the 1 is the n quantum number, and the s refers to the L quantum number. Of course, s corresponds to L equals 0. And in this case, m has to be 0, because remember that m has to run from minus L to plus L as an integer. For comparison with some later pictures, I've also plotted here this 1s orbital on a logarithmic intensity scale. This makes it a little easier to see what happens at larger distances, but of course it's not accurate. This is the accurate one, but this will let us see later on some comparisons. Here's the 2s state. On this scale, you barely notice any difference compared to the 1s state, but it is in fact significantly different. This is n equals 2, L equals 0. And to see that, we should look at the logarithmic intensity scale, because then you see here's the radial 0 in that function, and the function then goes through 0 and grows in magnitude again in probability density and then decays off. So this is what it actually looks like in a linear scale, but if we look on the logarithmic scale, we can see what's going on at these larger distances. The 2p state is exactly like what you would think for p states of atoms. So it's got two lobes, top and bottom, but we now have the radial dependence as well here, so it falls off exponentially with radius. And in the wave function itself, this would be a positive lobe and this would be a negative lobe. But of course, we're looking at the probability density here. And here we see a nodal circle that is pinched off the wave function. If we look at the other m values, all that happens is that we rotate this to the other two coordinate axes. So it's not really a different function, it's just in a different axis. The 3s state, again, on this linear scale doesn't really show very much. But if we put it on the logarithmic intensity scale, we can see what's going on. We've got two radial zeros here, as we would expect for that n equals 3, L equals 0 function. And then if we look at the 3p state, so that's L equals 1, again, the angular function has got a nodal circle that pinches off the wave function here. But because we have n equals 3 and L equals 1, we have to have another radial 0. And here's the radial 0 round here. And on a logarithmic intensity scale, we can just see slightly clearer what's going on. Again, we have pinching off in the middle, and we still have another radial 0. So this pinch off in the middle is from the L equals 1, and we have another radial 0 here. The other m values, minus 1 and plus 1, again just look the same, but on the other coordinate directions. Here's the 3D state. Remember, this L equals 2, m equals 0 state has got no nodal circles going through the poles, so it has two nodal circles pinching in here in these two directions. Because n equals 3, L equals 2, there's no other 0 in the radial direction. The necessary zeros are shown by these behaviors, not by radial behaviors. So they're zeros in angular behavior. And here's another 3D function, this time with L equals 2. And this has got two nodal circles, one going through the poles and one going round the equator. And there's no need for any further zeros in the radial direction, n equals 3, but we have our two zeros from the angular functions, these nodal circles pinching off the wave function. And we could go on like this to higher n's, but we will stop here at this point. So let's just summarize the behavior of the complete hydrogen solutions then we've been looking at. The overall size of the wave functions, first of all, becomes larger with larger n. We've seen that. It falls off as minus rho over n, essentially. And the number of zeros in the wave function overall is really n minus 1. It's a principal quantum number minus 1. These can be in the radial functions, but if we have L greater than 0, then we start to get fewer zeros in the radial functions and we get them in the angular functions instead. And the spherical harmonics, remember, have L nodal circles. Just a minor point here, you might think, well, these radial functions happen to have additional zeros at r equals 0 once L gets greater than or equal to 1. But this particular 0 is already counted because every time L is greater than or equal to 1, there's at least one nodal circle in the spherical harmonic, and that pinches off the wave function, so it already takes care of this 0 at r equals 0. So overall, the radial wave functions have n minus L minus 1 zeros, and the overall wave functions really have n minus 1 zeros. Just to summarize on these quantum numbers now, for the so-called principal quantum number, as we said, it starts at 1 and goes up in integer increments. The L quantum number has to be less than or equal to n minus 1, another way of stating the same as we said before. We already deduced that L has to be positive or zero integer. And we know the eigenenergies. We actually wrote down the formula before. For given possible values of n, the eigenenergies are minus the Rydberg over n squared. Note incidentally that the energy does not depend at all on the L or m quantum numbers. It only depends on the n quantum number.